This lecture introduces an overview of the second order differential equations. So if you have a second order differential equations, it's an equations involved the second, first, and the zeroth derivatives of a functions. A standard way of writing a second order differential equation is the second derivative of y, right, in terms of t, equals to a function f that involves t, y, and dy dt, which is the first derivative of y in terms of t. So in this chapter, we'll consider the second order linear differential equations, right? In which case f is a linear equations in terms of y and y prime. That means there will be no roots, no powers, no other function of y and y prime appearing in the formula of the function f here. Well, first, the standard form for a second order linear differential equation is usually people use L bracket y, that means linear differential equations of the function y, equals to a of t y double prime plus b of t y prime plus c of t y equals to g of t, where a of t, b of t, and c of t, and g of t are continuous functions on some interval. They are continuous on some interval here. And if you have two initial values, y at t0 and y prime at t0, then you will have an IVP. Okay. So again, this is a standard form of a second order linear differential equation. So if g of t is 0, that means the equation is a homogeneous equation. If g of t is not 0, then it is a non-homogeneous equation. So we call the function g of t here again, the functions of t on the right side is a non-homogeneous part, or in some modeling context, is the driving function. Well, let's talk about the existence and uniqueness theorem in the second order differential equations. If you consider an IVP of the second order linear differential equations with two initial values, yt0 and y prime t0, and then if b of t, c of t, g of t are all continuous on an interval from alpha to beta, then the second order linear IVP is this IVP here. For each t0 in this interval from alpha to beta, and y0 and y prime 0 are real number, then this IVP has a unique solution, y equals to yt. Again, we look at b of t, c of t, and g of t. Look at the intervals on which all of these functions here are continuous. And then if the t0, which is the initial value in terms of time, in terms of t, if t0 belongs to this interval, and the y0 and y prime 0 are all real numbers, then the IVP will have a unique solution. Well, let's look at the first example here. You have a second order differential equations, and I can try to figure this is b of t, this is c of t, and this is g of t, right? So I have b of t equals to negative 3t, c of t is 2, and g of t is 1 over t. Okay. Well, let's do some analysis on these three functions. So b of t is just a line, so it's continuous everywhere. similar to C of t, is continuous everywhere, but the G of t here is only continuous everywhere, but at t equal to 0. So that means if we combine all of this together, we know that the three functions continuous on negative infinity to 0 to positive infinity. So it's continuous everywhere. These three functions here are continuous everywhere except 0. Using interval notations, you know that it's continuous on the interval from negative infinity to 0 and union with 0 to positive infinity. Okay, well, let's look at t0. T0 in this case is 0. T0 equal to 0. And T0 is not, it does not belong to these intervals. Okay, so this means it's not in these intervals because 0 is the point where the function g of t is not even defined, let alone continuous. So if this is the case, T0 is not on the interval alpha to beta, then we can conclude that this IVP does not have a unique solutions. So this IVP specifically doesn't have a unique solutions, but if somehow you can pick a different set for the initial values, or you can come up with a T0 that is not 0, right? For example, if you can find an initial value at when T0 equals to 1, for example, then your IVP, the new IVP with new set of initial values when T0 is not 0, should have a unique solutions. All right, because 1 is in the intervals on which all the functions here are continuous. All right. Well, next, let's talk about something that's called the principle of superposition. Well, let's take a look at an example of a second order linear differential equations, a simple one. Y double prime minus y equals to 0. Okay. Well, at first, I want to guess one of the solutions for this differential equation is e to the r, e to the t. Okay. And the second solutions for this differential equation is e to the negative t. And this is my guess, but I need to make sure that my guesses are correct. So if y1 equals to e to the t, then in order to check whether this function is a solution, I need to find y double prime, right? So y prime equals to e to the t, y double prime equals to e to the t. Then I can plug e to the t into y double prime, and then y equals to e to the t, I get 0. So yes, this is the solutions. How about the second functions, y2? So for y2, I have y2 prime equals to negative e to the negative t. For y double prime 2, I have negative negative, which is positive e to the t. So then again, if I plug y double prime e to the negative e to the t, negative t, minus y, which is e to the negative t, I still have 0. That means, yes, the second function is also a solution. But now, what about when I take a linear combinations of these two functions? That means I take the first function multiplied to a constant c. c1 and c2 are constants. Are just real number, right? They're constants. So I want to know whether this new function, this linear combinations, is also a solution to this differential equation or not. Well, in order to figure it out, again, I just need to find. So I call this is y. Okay. And I want to find y prime. Y prime equals to c1 y1 prime plus c2 y2 prime. And c1 y1 prime is c1 y1 prime is e to the t, okay, plus c2 y2 prime, which is negative e to the negative t. How about y double prime? So y double prime, I just take equals to y prime, right? And then derivative of y prime. So this is my y prime, and I just need to find y double prime. So it's going to be c1 e to the t plus c2 times negative a negative, which is positive, e to the negative t. Okay. So in this case, I know that this is my y double prime. And which is the same as my y. So my y is c1 y1, which is c1 e to the t plus c2 e to the negative t. So this is y double prime, and these are the same functions. So if y double prime equals to y, that means this solutions here, these functions here, satisfy the original differential equations. So what I'm saying is, if you take the linear combinations of the two solutions of the differential equations, the linear combinations here is also the solutions of this differential equations. That means y equals to conclusions c1 y1 plus c2 y2 is also a solutions. And more generally, it is those general solutions to this differential equation. All right, so the first theorem in this lecture is saying that if you have y1 and y2 are the two solutions of a differential equations, then the linear combination c1 y1 plus c2 y2 is also a solution for any values of the constant c1 and c2. And as we know that once we come up with the general solutions as a linear combinations, we can just use the initial values to determine the value for C1 and C2 later if we have an IVP. All right. So we have two solutions. We can combine them using constants to come up with the general solutions. Now we talk about Wronskian determinants, or simply just Wronskian. So if we consider y1 and y2 to be two solutions of the same equations, right? And then the Wronskian is determined as, so the notation for Wronskian for the two solution y1, y2 is w bracket y1 comma y2 bracket is equals to y1 times y2 prime minus y1 prime times y2. Okay. Furthermore, if we given a pair of initial conditions here, then it's always possible to choose a constant c1 and c2 so that the functions c1 y1 plus c2 y2 is general solutions. And these functions here is also satisfy these equations as we already discussed, right? And then the initial condition t0 y 0 and t0 y prime 0. This is the general solutions if and only if the Wronskian value of y1 and y2 is not 0 at t equals to 0. Okay. Again, to summarize this, you have two functions y1 and y2, and then you have the two initial values yt0 and y prime t0. So the differential equation, or the IVP, we have the solutions, right? If and only if the Wronskian value of y1 and y2 is not 0. So the Wronskian determinants helps us to determine whether the solutions y1 and y2 are linearly independent, which means the two solutions functions are linearly independent on their ranges. So if they are linearly independent, that means they span the whole entire solution set for the differential equation. If they are not linearly independent, they are not spanning the whole solution set for the differential equations. So determine the Wronskian value is important when you're trying to figure whether the solution that you found contains all the solution sets. Okay. Another reminder, if the Wronskian is not 0, then y1 and y2 are linearly independent. If the Wronskian is 0, then y1 and y2 are linearly dependent. So first, we want to compute, just look at an example, right? We want to compute the Wronskian for the following pairs of functions. So the first pair, the first functions, just want to remind you that if you have 1 and t, so 1 is y1 and t is y2. Okay, so if I have y1 is 1, y2 is t, then I can figure y prime 1 is 0 and y prime 2 is 1. Okay, then the Wronskian of yt, 1t, equals to y1 times y2 prime minus y1 prime times y2. So y1 is 1 times y2 prime, which is 1, minus y1 prime, which is 0, times y2, which is t. So the result is 1, and it's different than 0. That means t and 1 are linearly independent. The functions 1, y equals to 1, and y equals to t are linearly independent. Okay. Well, go to the next pair. You have cosine of 2t and sine of 2t. Again, y1 equals to cosine of 2t, and y2 equals to sine of 2t. So for y1, I can find y1 prime equals to negative 2 sine of 2t. And I can find y2 prime equals to 2 cosine of 2t. And to find the Wronskian of these two functions here, as you can see that I was using the cross multiplications technique. Multiply 1 to 2 prime and minus 1 prime to y2. So this is going to be equals to cosine of 2t times 2 cosine of 2t, right? Minus negative 2 sine of 2t times sine of 2t. So this is going to be 2 cosine square of 2t minus 2 plus 2 sine square of 2t. So there will be 2 times cosine square 2t plus sine square of 2t, which will give you 2 times 1 is 2, and it's different than 0. So 2 is not 0. The conclusion is, yes, these two functions here are linearly independent. All right, go to the next example. Well, we have y1 equals to e to the rt and y2 equals to t e to the rt. Okay, well, we can find y1 prime equals to r e to the rt and y2 prime equals to e to the rt plus t r e to the rt, using the product rule here. And again, you want to find the Wronskian of these two. You're going to use the cross multiplication technique, right? Multiply this two and minus this product. So that will give you y e to the rt times e to the rt plus t times r times e to the rt minus r e to the rt times t e to the rt. And we will have it here. We'll have, this is e to the rt times e to the rt, right? And then you have e to the 2rt plus t r e to the 2rt minus t r e to the 2rt. So that will give you, this gonna cancel this out. So then the result is just e to the 2rt. And e to the 2rt, as you already know, that is an exponential function. It's always positive for rt and r. That means e to the y equals to e to the rt and y equals to the t e to the rt are linearly independent. Because all the Wronskians of all of these pairs are not 0. Okay, so if you determine the two functions are linearly independent, that means if those functions are solutions to differential equations of the second order, they span the entire solution set for the differential equations. So that's the idea of fundamental set of solutions. So if, again, y1 and y2 are linearly independent, right, we can determine that using the Wronskian. Then they form a fundamental set of solutions for the second order differential equation. In other words, the two solutions are form a fundamental set of solutions of a DE if their Wronskian is non-zero. So we use the Wronskian to determine whether two solution functions form a fundamental set of solutions. So fundamental set of solution means the two functions there, the linear combinations of the two functions y1 and y2 will span the entire solution set for the differential equations with all initial values. All right. Well, let's look at the next example here, right? And you have two solutions, y1 and y2 for the differential equations. And you want to know if these two solutions here forms a fundamental set of solutions. And fundamental set of solutions with arbitrary constants C1 and C2 is a general solution for the differential equation. All right, so we just need to find the Wronskian of e to the negative 2t and e to the negative 3t. Okay. It's gonna, so y1 equals to, so I just want to write down y1 is e to the negative 2t. So y1 prime is negative 2 e to the negative 2t. And I have y2 equals to e to the negative 3t, then y2 prime equals to negative 3 e to negative 3t. Okay. And then you can use the cross multiplications to figure the Wronskian of these two functions. So it's going to be negative 3 e to the negative 5t minus negative 2 e to the negative 5t. So that will give you negative 3 plus 2 is negative e to the negative 5t. And again, because this is the an exponential function, so it's always positive for all t. That means, yes, these two functions y, yes. E to the negative 2t and e to the negative 3t, form a fundamental set of solutions. Sometimes you can put this in a form, in a set form, right? Okay. Well, let's look at the next example. You have y1 equals to t 1/2, right? Then y1 prime equals to 1/2. T is negative 1/2. You have y2 equals to t of negative 1. That means y2 prime equals to negative t negative 2. And you use cross multiplication to find the Wronskian of these two functions. 1/2 so the Wronskian will be equals to t 1/2 times negative t negative 2 minus 1/2 t of negative 1/2 times 2t of negative 1. Okay, and you will have t to the negative t to the negative 3 over 2 and minus 1/2 t over to the negative 3 over 2, and that will give you negative 3 over 2 t to the negative 3 over 2. And this functions here, since it has the power, the negative power, so this functions here will be different than 0, will be defined, right? So this function is discontinuous at t equal to 0, but other than that, it will define everywhere and it will be not 0 everywhere. So this is not 0 for t is not 0, right? When the function is defined, then this functions here, an exponential function, will be not equals to 0. Okay. So what does it mean? That means yes, the set of the two function t of 1/2 and t of negative 1 forms a fundamental set of solutions to this differential equations right here. And again, in order to determine the solution, particular solutions, you need to use the initial value when t is not 0. Okay, so if the two function forms a fundamental set of solutions, that means you can say that the linear combinations y of t equals to c1 y1 plus c2 y2 is general solutions to the differential equations. And then you can determine c1 and y and c2 using initial values that are given. All right, so this lecture again introduces the second order differential equations. It introduces general form of the second order differential equations. It introduces the existence and unique theorem. How can you determine if an IVP would have a unique solutions? And you know that if you confine two solutions to a second order differential equation, the linear combinations of the two solutions is also a solution, and is often called the general solutions. And if you find the two solutions and you want to determine whether those solutions span the entire solution sets for the differential equations, means if you use the linear combination, all the linear combinations of those two solutions will describe the solution set of a differential equation, then you want to use the Wronskian determinants. So once you determine the Wronskian determinant of the two functions, the two functions will be linearly independent if the Wronskian is not zero. If the two functions are linearly dependent if the Wronskian equals to zero. So if the Wronskian equals to zero, then the two functions do not form a fundamental set of solutions. But then if the Wronskian is not zero, then the two functions form the fundamental set of solution for the differential equations. And the fundamental set of solutions is a set of solutions that can span the entire solution set for the differential equation. Okay. So in other words, you can say that if you're given any initial value, the fundamental set of solutions can determine the particular solutions for that IVP. Okay. All right, here you go, an overview of second order differential equation.